So in the last video of quantum field theory, we talked about how to calculate the probability that two electrons come in our system with some momentum k1 and k2 and leave the system with momentum k3 and k4, which essentially was just boiling down to calculating this right over here, where this is some initial state and this is some final state, where the initial state contains two electrons and the final state contains two electrons. And we found that this matrix element, that's what we call this, a matrix element, is proportional to this quantity right over here. So phi x1, dot dot dot, phi xn, and then phi y1, dot dot dot, phi ym. And we call this over here the endpoint time-ordered correlation functions. And basically, we have to calculate this big thing right over here, take a bunch of integrals, a bunch of Fourier transforms, and that'll give us the probability that this process happens. And we can replace the initial state and the final state with whatever particles we want to choose. So in quantum field theory, like the main thing that we really want to calculate in quantum field theory are these endpoint correlators, okay, the time-ordered endpoint correlators, because it is these things that contain to the information of our interacting theory. So the question becomes, how do we calculate these things? We can start off simple and consider the vacuum expectation value of the 2-point time-ordered correlation function. Say that 3 times fast. And we've actually seen this thing before in our video on propagators. We know that this is actually the Feynman propagator, which represents the probability that a particle propagates from point A to point B in time t to t prime. But that was for free field expressions. If phi is free, it's going to actually be equal to something like this. This thing over here is going to be a Green's function of the Klein-Gordon equation. So if you plug this into the Klein-Gordon equation, you would get a delta function as a result. But we don't have free fields in the LSE reduction formula. We have interacting fields. So the question becomes, how can we calculate the thing that we calculate for free fields, but for interacting field? What we could do is we could expand our interacting field in a perturbative series of free fields. That'll take too long. So what we could do is do what I like to call a sleight of hand trick. We could actually get away with working with the free fields. Like we can pretend that the interacting field is a free field if we adjust some things. And that whole kind of adjustment is what we call the interaction picture, which is the subject of today's video. So how do we derive this picture? Well, first of all, we want to look at the quantum field at some moment in time. So phi of tx, right? This is going to be an interacting field, and the interacting field has a very complicated structure. But we could look at a single time slice of the interacting field and expand that in terms of a Fourier decomposition, right? So you guys might look at this and say, oh, so we're saying that this is a free field. No, right? This is simply in some moment in time called t naught. We're not saying that phi of tx is this. Then that would be a free field. But instead we're saying that we are looking at the interacting field in some moment in time and expanding it, right? So say like here's some moment in time, t equals t naught. And we are expanding this in terms of a Fourier series, pretty much. Now what we could do is we can say that phi of tx equals e to the iht minus t naught, phi of t naught x, e to the minus iht minus t naught. You guys might wonder where we get this from. Well, this actually comes from quantum mechanics. So remember in quantum mechanics, we often want to calculate the expectation value of some operator. So say we had some operator O, and we want to find the expectation value of this operator. But let's say that our states depend on time. Okay, so our states depend on time. Well, if our states depend on time, right, we know that it's going to evolve according to the Schroeder equation, which has a unitary time evolution, meaning that phi of t equals e to the minus I h t phi of t equals 0, right? So you can just write this out as phi of 0 e to the I h t, the operator, e to minus I h t phi, so I'm saying phi, I mean psi. And then we can say that, oh, let's just define O of t as e to the I h t, O e to the minus I h t. And then this just becomes psi of 0, O of t, psi of 0. So basically, we can calculate the expectation value of some operator with states that time evolve, as treating the states as stationary in time, as in they don't time evolve, and let the operator take the time-dependent terms. So we're calculating the exact same thing, but we're just shifting some things around, right? And we call this over here, we call this the Heisenberg picture. In the Heisenberg picture, our operators evolve, and our states don't evolve. And we call this over here the Schrodinger picture, which is more commonly used in quantum mechanics, where the states evolve and the operators don't evolve. So basically, for example, the momentum operator, p hat equals minus I h bar d over dx, it does not time evolve, right? You don't like say, oh, p hat, voice crack, you don't say p hat of t, right? But we could technically do that. So that's why we have this expression right over here, since phi is an operator. So when it evolves in time, we can use this equation right over here. Then we put an h right next to it, which indicates that it's in the Heisenberg picture. So we're letting the time evolution be in the Heisenberg picture, where the operators evolve with the full Hamiltonian, which means the Hamiltonian here contains the free term and the interaction term as well. And we use a t naught here since phi starts out at t naught. If t naught equals 0, then we just have like the normal thing that we had before. So there are multiple pictures of quantum mechanics, right? Let's look back at the this inner product over here. You could also make it such that the operator evolves as if it was free, and the states evolve as if they are interacting. Right, so again, we know that this equals e to the I h t phi of 0, or psi of 0. And we can split out the Hamiltonian into a free part and the interacting part. Now, just to clarify, what part we call free and what part we call interacting does not actually matter in practice. We should just call the interacting part the complicated part, okay? The part that is not exactly solvable. So it's arbitrary how you split it, but like making the interacting part be for the case of the phi4 theory, making like this the interacting part, we have phi4 over 4 factorial, and then like d to the 4x. That's what we typically call the interacting part for the phi4 theory. So if you made this split over here, we will then have this over here for the time evolution of psi of t, where we define the interaction Hamiltonian as h prime, since it's easier to write. And then, by doing some more things, we can then do some rearranging here, right? Giving us, we can then absorb the interacting part into our states, and then the free part into our operator. And this defines psi I of t, and then the covector form. And this defines O I of t. And we call this new product over here, this new product, we call it the interaction picture. The interaction picture. And with the interaction picture, we let our states evolve with the interacting part of the Hamiltonian. And we let our operators evolve with the free parts of the Hamiltonian, which means that psi I of t equals e to the minus I h prime t psi I of 0, or just psi of 0, doesn't really matter. O I of t equals the same thing we had before, but with the free part of it. So before, in the Schroeder picture, we let the states evolve with the full Hamiltonian, right? So for the Schroeder picture, we just had IHT, right? This was the Schroeder picture. So we used an S for the Schroeder picture, where H was the full Hamiltonian. In the Heisenberg picture, what happened was that these states did not evolve at all. So psi of HT is equal to psi of H0. That's a Heisenberg picture. And then in the interaction picture, what happens is we use an I for the interaction picture. In the interaction picture, we let these states evolve with just the interaction part of the Hamiltonian, the complicated part. And the operators evolve with the free part, okay? So why do we use the interaction picture? Well, you know what else is an operator? Our quantum field, right? So the interaction picture, we can let the quantum field, phi of tx, is going to evolve with e to the I h naught t, and then minus t naught in this case, if we start out at t naught. So then phi of t naught, e to the minus I h naught t minus t naught. And we call this the interaction picture for our quantum field. This evolves with the free Hamiltonian again. And this means that this field itself is actually a free field. The interaction picture field for the interaction quantum field is a free field. That's why the interaction picture is so useful. See why it's a free field? Note that again, phi of t naught x can be expanded in terms of Fourier modes like this over here. And then, so it looks like this, right? And then we're evolving it with the free part of the Hamiltonian. So it's evolving with the free part. So it looks like it's free at t equals t naught. And it continues evolving as if it's free. So the whole thing is pretty much just the free field, right? So the interaction picture field, phi I, that's a free field. Whereas phi h is an interaction field. Okay, guys might ask, okay, what is phi of t naught x? Well, that's just a moment in time, so it's not really anything. And we wanted to find out the endpoint correlators. And it would be nice, right? It would be really nice if we could somehow use the interaction picture to replace this over here, where these are all in the Heisenberg picture, since they are interacting fields, and replace them with the interaction picture fields. How can we do that? Well, if we assume, let's assume, okay, we're getting some math words right now. Assume that there exists some time t equals t naught, such that phi h of t naught x equals phi I of t naught x. So basically, this is saying that we're assuming that there exists some time t where the free field has the same form as the interacting field. Usually, we actually assume that t naught is like asymptotic, okay? Now, what are the implications of this? We can write out phi of t naught x, this over here. We can isolate this, right? By multiplying both sides by e to the minus I h naught t minus t naught. And then we'd have phi of tx, and then e I h naught t minus t naught, and then we can just plug in this in right over here, and that'll give us that phi h of tx, this equation right over here. Now we define this as u of t naught. We define this over here as u conjugate t naught, which means that we can write out the Heisenberg picture quantum field equals u conjugate t naught phi I tx u of t naught. This is our endpoint correlator thing where we have like phi like x1 like y1 whatever. We can just these were all in the Heisenberg picture, right? We can just use this equation to get the free field inside of this expression over here. Now we can get an equation of motion for u of t naught. So we can just put u of t naught into the Schroeder equation. Again, we can't just say that this is going to be e I h prime t minus t naught, because the Hamiltonian and the free Hamiltonian do not actually commute. So, and then if you were to expand out the Hamiltonian, you would end up getting e to the I h naught t minus t naught h prime e to the minus I h naught t minus t naught, and then times the unitary operator. You get the same thing out again. And this is just going to be the interacting Hamiltonian, right, in the interaction picture. So you can actually write this out as h prime I, so h prime I, then u of t naught. We know that the interacting Hamiltonian, right, contains a term of lambda phi to the 4 over 4 factorial. Technically, we should integrate it as well, but let me just omit that part. So phi contains the interacting field. But the interacting Hamiltonian, the interaction picture Hamiltonian, the actual free field expressions over here. So by using the interacting Hamiltonian, we can put the free field expressions into that part, which means that we can solve this equation for u of t naught, and u of t naught will contain just free fields. This equation is actually pretty easy to solve. Its solution is going to be e to the minus I integral of dt prime of hi prime of t prime from t naught to t. So this is the solution. You could convince yourself that this is a solution. You basically just like treat u of t as like some normal variable, then like it's just a homogeneous differential equation. So this is the solution. Technically, we should add some time ordering factor in the front, but we're going to talk about that part later on. So for now, this is a solution to this equation. So now we can kind of connect some things. So again, at the start of the video, remember that we want to calculate this quantity over here, and then now we can use this new formula that we derived, plug that inside, and then we get this formula for the time ordered product. All we did was we plugged in the Heisenberg expression fields with the free fields that are in the interacting picture, and then we can note this property over here. You guys can hopefully convince yourselves of that property, and then we get this right over here. Almost done, okay? We now only have free fields in here. I don't know what happened to the other free field. It should be right over here. So there should be another free field. Phi I t prime x prime right over there. Okay? And we're almost done, but we're not completely done yet, because yes, we have free fields now, but we have the interacting vacuum, okay? Free fields don't really act on the interacting vacuum in a very nice way, right? For the same reason that the interacting fields don't act on the free vacuum in a nice way. So is there a way that we can somehow replace the interacting vacuum with the free vacuum? The answer is yes. So we're trying to write out the interacting vacuum in terms of the free vacuum. So to do that, what we can do is time evolve the free vacuum, with the e to the minus iht time evolution term, where h is a full Hamiltonian. We can then insert a completeness relation, which is this one over here, where n is some energy eigenstate. Since energy eigenstates are typically discrete, you can write it like this over here. So now what we can do is we can act this term e to the minus iht, we can move that over here and let it act on this energy eigenstate. And then we can note that would give us this term over here, because if we're to expand e to the minus iht in a Taylor series, so imagine if you were to take e to the minus iht, right, and we want to act it on this over here, so we move it here to act on this. We can expand this in terms of a Taylor series, so that's going to be 1 minus ih, and then ... acting on n, which gives us 1 minus ih acting on n plus ... and then h acting on n will give us, if it's an energy eigenstate, it'll give us e, and then acting on n, right? And this is just the Taylor series for e to the minus I e n t acting on the energy eigenstate. So that's why we get this e to the minus I e n t over here. And then here we have the inner product between the vacuum state and the energy eigenstate. And then basically what we can do now is explicitly carry out the sum, which will be this over here, plus the higher order terms, right? We have the interacting vacuum state here because the lowest energy eigenstate is going to be the interacting vacuum state, right? Here are the energy eigenstates. These are eigenstates of the full interacting theory, FYI. So rearrange this formula to solve for the first term in the series. Okay, so the first term in the series is going to be this minus the other, where again, the other is just the higher order terms in the series, the terms for n is not equal to 0. Then what we can do is in a clever trick, we can take the limit as time approaches imaginary time, infinity. This is what's called a Wick rotation. We do that on both sides. So this step is kind of tricky. I'm going to explain how it works. So basically, we found that this equals this, and then be rearranged for this over here, okay? And then once we've rearranged this over here, we can just divide by this term over here. We can divide both sides by that term. Pretty much this like would be like over here if we divided it. So once we divide both terms, we can isolate for this interacting vacuum. Then after we divide by both sides, we can take this limit over here. The other term, the higher order terms, drops out when we take the limit. And the reason as to why that happens is because, so the higher order terms look like this generally, right? And we know that as n approaches infinity, this part is going to get larger, right? And what this imaginary time thing does is that it's saying that we're taking the limit as t approaches infinity times 1 minus I epsilon. And if you were to plug that in here, we'd have e to the minus I e n times infinity minus infinity I epsilon infinity. If we were to distribute that out, right, what you'd end up having is e to the minus I e n infinity, and then e to the I times I is minus 1, times 1 is 1, times 1 is minus 1, is minus epsilon infinity. So we're going to get this, pretty much, okay? And this part is going to oscillate, contain sinusoids, whereas this part is going to decay. So this part is going to go to 0, so this whole thing is going to go to 0. Well, really, there should have been an e to the n over here. There should be an e to n over here. So as this gets bigger, this whole thing gets bigger, so this whole thing gets smaller. I know I explained that very terribly, but I hope it makes at least a little bit of sense, right? As e to the n goes bigger, since there's a negative sign here, plus this infinity over here, this whole thing is going to get smaller and smaller and smaller. So yeah, there should have been an e to the n over there. So that's why the other terms will drop out. Derivation t naught into the exponential. We can do this since we're working with asymptotic times, so adding a small perturbational effect the expression overall, since we're taking the limit as t approaches imaginary infinity. So by doing this, we can just focus on this numerator right over here, right? Focusing on the numerator, this is in the numerator over here, okay? And now we can actually rewrite this as t naught minus t e to I naught of this. And the reason why we are rewriting it as that, so this is just going to be u of t naught minus t acting on the vacuum state. That's because u of t naught was defined like this. So by swapping the terms in the function, that corresponds to swapping these together and then swapping the insides together as well. And then by changing the sign of t, we get this over here. So that's why this is equivalent to u of t naught minus t acting on the vacuum state. So this means that we can relate the interacting vacuum with the free vacuum with this formula right over here. Now, I know this part does not look very clean, so let's clean this up a bit. So what this says is e to the minus IH times t plus t naught, and then times e to the I h naught t plus t naught. And that is all being divided, or then times the vacuum state again. And that's all being divided by e to the minus I e naught times t plus t naught. Okay. So that's what this is saying right over here. And then basically we said, oh guys, look, this is just the same thing as u of t naught minus t, right? And that allows us to say this over here, right? And then of course we have to apply the limit. So now we've pretty much done what we need to do to derive the Gell-Mann and Low formula. So you can just plug this thing, we can plug that into here, right, of this really long time ordered product that we derived previously. So we can note that the covector of the interacting vacuum is going to be equal to this over here. Note that we have e to the minus I naught t minus t naught. I think the reason as to why it's that way is because if we let time be imaginary time, then the complex conjugate of this over here is just going to be e to the I e naught, and then minus t plus t naught. And that's the same thing as this over here if we were to like distribute the negative sign, pretty much. By plugging all those things in, we can find out this right over here, or the really big term is, you can probably infer what that refers to. And now we have this ugly term right over here. So what we could do is note that the inner product of the interacting vacuum state with itself is just this over here. We get that by literally just multiplying this by itself. And then we can say that, oh, let's just define this to be normalized, right? So if this is equal to 1, well, then what that means is that we can divide this really big term with all the other things by 1. And if you were to divide those things by 1, that means that many things cancel out. So that means that this will cancel out, and this will cancel out. But these don't cancel out. Instead, these go to the denominator. And technically speaking, these should be sandwiched between the free vacuum. So basically, this time-ordered product of the Heisenberg fields is equal to this term right over here. So just zooming in so you guys can see what this says. We just have divided it by the inner product of the unitary operator, essentially. All right, so we have this relation right over here. We can use the property where u conjugate of t naught is just u of t naught t. So conjugating the unitary operator just flips the inputs, okay? And then what we can do is we can choose t naught to be infinity, this t naught to be infinity, then this t naught to be minus infinity. That might seem a bit weird, but it kind of makes sense since this is saying that we time evolve from t naught to t, then from t to t prime, then from t prime back to t naught, right? But like actual particles, like time does not like go in a loop, it goes forward. So it would be better to choose this t naught to be different from this t naught over here. So to choose this t naught to be minus infinity, and then for this t naught to be infinity. And that's just going to give us, oh, also what I did here. I should have said what I did here. So basically what we did here was we just moved the unitary operators in front of our fields. And this is because of the time ordering. The time ordering will allow us to move the things in our expression. So this will just give us the inner product of t of u of minus infinity and then infinity. Because this is minus infinity, that probably gets to t, and this goes from t to another intermediate t prime, and then t prime to infinity. This is the same thing as u of minus infinity and infinity, and then acting on phi tx vi t prime x prime, and then closing bracket. We can do a similar thing for this part over here. If we were to zoom in, we can note that the conjugate just flips the inputs. So this is the same as minus t and then t naught. Okay, so then we can say, oh, okay, so here we're going from minus t to t naught, then back to minus t. Doesn't really make much sense, right? So we could let t naught be some intermediary, and then let here be minus infinity, and this over here be infinity. It's kind of like a piece of notation. I'm not even sure if that argument is completely correct. But that would just leave us with the inner product of the unitary operator from minus infinity to infinity. Okay. And then that will leave us, we could just like move this back to the right. We would then have this formula right over here. This should have been the free vacuum. I'm not sure why I wrote this as an interacting vacuum. These should have been all the free vacuum. All this should be the free vacuum. So now this formula over here, then we just expanded out the formula for u of minus infinity, infinity. And then technically speaking, we should have a time ordering term, like right over here. But we already have one here, so it doesn't matter. But we do have to input it right over here. As to why there's a time ordering term right in front of the unitary operator, we'll talk about that in the future video. It's due to the fact that some things don't commute. But just for now, let's just have it there. Now we have this form over here. We call this the Gell-Mann Low Theorem. And this theorem relates the quantum fields, the endpoint correlators of the quantum fields in the Heisenberg picture to the endpoint correlator of the free fields in the interaction picture. So this formula is really nice, right? Because it's telling us, in order to calculate the time-ordered inner product of, interacting quantum fields, we can actually instead use free fields. This is the trick I was talking about in the beginning of the video. We can actually use the free fields here with the free vacuum, as long as you multiply that product by that unitary time evolution term, and then divide it by the same term. Okay, you guys might wonder, wouldn't these like cross cancel or something? It's not going to cross cancel. The reason why it's not going to cross cancel is because you can't like move this in front and then move this on the outside and this on the outside, so it would cross cancel. Now the question actually becomes, right? We remember in the start of the video, we said assuming that the interacting field equals the free field at some time t, then blah blah blah, right? Now is that assumption actually correct? It turns out that assumption is not correct, and that there does not actually exist a u that relates the interacting field with the free field, which means that this term over here, this u of minus infinity, does not actually mathematically exist, and as a result, this whole thing will diverge. Dun dun dun!